I sure hope that everyone is having a great day today. I'm Lawrence Snyder, and I'd like to welcome you back to the High Performance Fundamentals YouTube channel. This will be the second video in my Automotive Electrical Systems video series. Today we'll be covering series circuits, parallel circuits, and the combination of the two, the series parallel circuit. I'll be explaining terminologies and equations, and I'll be providing you with some examples and a interesting analogy for clarification purposes. Now, before we get started, I'd like to make some amendments or some clarifications to some of the information that I provided in my first video, video number 1. All right. A couple of things real quick. One was I talked a lot about the digital volt ohm meter, or the DVOM. What I want to make clear is that that can also be known, or it is widely known, as a multimeter. Whether you're shopping for a multimeter or a digital volt ohm meter, DVOM, either terminology or either nomenclature, that would be accurate. Just make sure you're shopping for something for the automotive application, because there's all different types out there. Make sure it's automotive application based or specific, right? Okay, so other than that, there's a couple other things. I noticed when I'm watching the video back, and keep in mind that I am by no means a videographer or a photographer, and this is literally like my second video ever. I realized that some of the charts and the information I was pointing to and talking about was really difficult to see. So what I want to do is, in particular, it was Ohm's law in a modified version of Ohm's law, and Watt's law in a modified version of Watt's law. What I want to do is I'm going to take a minute. I'm going to go ahead and put an image in here for Ohm's law and the modified version of Ohm's law. And then I'm also going to put in the image of the Watt's law and the modified version of Watt's law here. Now in the video number 1, I explain how I get from the actual Watt's law to the modified version, and how I get from the Ohm's law down to the modified version of Ohm's law. You can watch video 1 and it gets into pretty in depth as to how I came up with the modified version, if you will, and why I use that. All right, now with that being said, at the end of the video, close to the end of the video, I mentioned point type ignition systems, and in particular I mentioned adjusting dwell. All right, a lot of or I should say that the information that I provided there was accurate, except for when I gave a range of specification for adjusting dwell on a V8, a 6-cylinder, and a 4-cylinder. The adjustment range that I had given for the V8 was 28 to 32 degrees. In most applications, that is still, I'll stick to that. That's pretty accurate. It may be slightly different than that, and like I said, refer to the manufacturer's specifications, for your application. The 6-cylinder I gave, let's see, that was 34 to 38 degrees. Also fairly accurate. Like I said, always, refer to the manufacturer's specifications. But on the 4-cylinder, although what I had said was 52 to 56 degrees is a decent average range. And although that is accurate for some models, what I found was that on certain models, it's way off. And I got to thinking about that after I'd watched the video, and a couple days later, it hit me like, I'm not so sure about the 4-cylinders. After I'd already put it on the video and I talked all about it. So I went back and I checked. So I went ahead and, believe it or not, this is a motor handbook. This is the 54th edition from 1977. Yes, I still have it. And I opened it up and I got to looking through there. And what I found was that on a lot of the European, German models, the Japanese models, the specification that I gave, 52 to 56 degrees, is pretty accurate. But then I got to looking at the American-made models, the Chevrolets and the Fords. Not even close. Okay? So, like I said, although at this point I kind of wish I wouldn't even have brought all that up, but just to clarify, 28 to 32 degrees on a V8 is close. On a 6-cylinder, 34 to 38, that's fairly close also. On a 4-cylinder, I had said 52 to 56. And on a lot of the European and Japanese models, that would be pretty accurate, but it sure doesn't cover the domestic manufacturers, the Chevrolets and the Fords. Okay, so I just want to get that out there. Moving forward, as I do the next video, like for example, in this video will be video 2. When I do video 3, if I find inaccuracies or things I need to clarify, I'll put that in video 3. So as to try to keep these videos as accurate as possible, because that is my goal. All right, so from there what we're going to do is we're going to get on to It's a series circuit, the parallel circuit, and a series parallel circuit. I'm going to show you over here basically the textbook definition of these, and then we're going to move on to modified versions and some things that will help clarify that quite a bit. Okay, so we're going to start with that. Okay, so here we have three examples of what I like to call the textbook version of a series circuit, a parallel circuit, and a series parallel circuit. Okay, what we have shown here is a symbol for a battery and a symbol for three resistors. Down here, same thing, battery, three resistors. Same thing, battery, three resistors. Okay, basically the resistor is also known as the load. For example, a fan motor can have resistance, so therefore it might be shown as a resistance. A resistor, an actual resistor, of course, has resistance. So basically anything that provides a resistance to the current flowing through the circuit, okay? So it's showing the arrow, the direction of current flow is shown by the small arrows that you see there. And in this case, it's showing current flowing from the positive side of the battery through each resistance back to the negative side of the battery, makes a big loop. Okay, series circuit is fairly easy to understand. Basically, all the current is flowing through a resistance or the load and then back to the battery. Whether it's one resistance or two or three, they're in line. It flows into one, out of it, into the next, out of it, into the next, out of that, back to the battery, right? And like I said earlier, we're going to get into a much simpler, and what I feel to be a much easier to understand example. And we'll go through those and some analogies to make this much easier to understand, so just kind of bear with me. All right, so on a parallel circuit, what do we have here? It shows that we have the same thing, direction of current flow. And as you can see, it shows arrows leaving the battery, going over to the first splice or junction, or sometimes maybe called a node. But let's say the junction or splice, onto the second junction or splice, then onto the third resistor. It shows that the current is flowing through the third resistor, through the second resistor, through the third resistor, all three of which are flowing current back to the battery. One thing to consider here in all of these circuits is that it is a loop. It's going to leave the battery, it's coming back to the battery. If current leaves, it's coming back, right? So just think of it as a loop. Each circuit is a loop. Positive, negative. Round and around we go. Same way as I'd mentioned in the first video, if you were to connect the positive and negative circuits together on a battery, like I said before, never do that, but that is completing the circuit, okay? The difference is instead of just jumping one to the other, we're going through the load. We're going out of the battery, through a resistance, the load, like I said, the fan motor, the fuel injector, the horn, whatever the load is, we're going through that load, we're powering that load, current's flowing through that load, and then coming back around and back to the negative side of the battery where it can basically just continues the cycle, on and on and on. As long as current is flowing through the circuit, it's non-stop, just keeps going, okay? When you interrupt a circuit with a switch or, you just take a wire loose or unplug a connector, then that current flow stops, it ceases to flow, okay? So this does illustrate, and it's good in one way, that it does illustrate that by the direction of the arrows shows you that all the current leaving the battery then goes back to the battery. All right, so in a parallel circuit, basically we have current leaving the battery. As I'd mentioned, it goes over and basically splices off or branches off into three separate resistances. At that point, they come back to the battery, and the cycle continues. In a series parallel circuit, basically what you have is instead of it branching off into three different resistors, shown in this example, we're going to go through a set resistance first. So now we have a series circuit because all of the resistance or all of the current flow, not resistance, but all of the current flow is flowing through one set resistance, okay? All of it is flowing through here. So this part of the circuit is a series circuit. All the current is flowing through that circuit. Then we go down line and we branch off into a parallel circuit where we are now branching off. So now we're going to branch off into resistor number 2, resistor number 3, or resistance number 2, resistance number 3. So this could be a physical resistor, and this could be 2 fan motors, for example. And then from there, the current is going to flow back to the battery, starts the loop over again. So series, everything flows through the resistances, straight through it, no branches, right? In a parallel circuit, the current flows, branches off into various loads, 1, 2, 3, there could be 5 of them, 6 of them, whatever number, right? So it's going to branch off. And in a series parallel, you're going to have all the current flowing through one load or one resistance and then branching off. So series, parallel, okay? Like I said, these are what I would call textbook examples, right? Okay, great. In my mind, though, that's great, but I'd like to see things. You're not going to see this in an automotive electrical circuit, okay? you're going to see more like what I've drawn over here. And we're going to move on and get to that real quick. And then we're going to, like I said, my goal here is to make this easier to understand. And I'm not so sure that that really does a good job of that. So let's move on to some examples that I've got here. Then we're going to get on to some equations. And then we're going to start to really break it down. We're going to modify some stuff. We're going to make it even easier to understand. We're going to make it to where you can really wrap your mind around this, all right? Okay, so here I have drawn the same series, parallel, and series parallel circuits. All right, these are more like what you're actually going to see in a wiring diagram. Like I said, these are textbook. This is more real world, all right? And here we have in this series circuit, right? Here's a symbol for a battery. It's a 6-cell battery shown in a battery case. Here's a negative post on the battery, or the negative side, and a positive post, or the positive side. From there, we're flowing all of the current through an inline ammeter, then to a fuse, then to both motors. In this case, they're going to be fan motors, and there's a reason for that. And then to a ground, all right? And then through the chassis, from the ground back to the battery, all right? That's typically what you'll see. I also want to make clear, in the textbook versions over here, they show basically every circuit looping back around to the battery. Well, in effect, that is what we're doing, but we're doing it through the chassis. And the way we can do that is the chassis itself is very conductive. So the current will flow into the chassis, through the battery cable, and negative battery cable, and back to the battery. So therefore, the reason we do that is because if you think about it, if every electrical circuit in the entire car went directly back to the battery, at the battery, you might have 200 ground wires coming off the battery. Imagine how busy that would be. You wouldn't be able to see the battery. Not only that, the volume of battery cables or ground cables would be such, there'd be so many, that it would be extremely expensive. It would make the vehicle weigh a lot, and it would be, just a total clutter. I mean, the amount of clutter, there'd be wires going everywhere. So we use the vehicle's chassis, which could be the frame, the unibody structure, some portion of the chassis we're going to use as our ground bus, if you will. All right. Anyhow, so I want to make that fairly clear. But here's a series circuit, right? All the current, right, or all the voltage and current is flowing through the ammeter, through the fuse, through the first motor, into the second motor, through the second motor, and then to the chassis, and then back to the battery in series, right? One after another, right? In series. Here's a parallel circuit, right? Very similar scenario, but the difference is this. Instead of it coming out of the fuse and going into one motor and then another, we're branching off right here, all right? This is going to be called a splice or a junction, sometimes even known as a node, right? And then it's going to branch off with two legs or two branches, each through the motor separately, and then both to the chassis, and then back through the chassis, through the battery cable, back to the battery, right? This is a parallel circuit. Here we have a series parallel circuit. Well, basically, like I said earlier, but all this really is this is just going to be a combination of the two. So we come out of the battery, positive post, come out of the battery through the positive battery cable or the positive cable. We go into the ammeter, inline ammeter, through the fuse, through the first resistance. Then we branch off into both motors. Then both motors ground to the chassis, back through the battery cable, and back to the battery. Series circuit, parallel circuit, series parallel circuit. Right? This is much more indicative of what you're going to see in a wiring diagram, okay? And in most cases, I can't say every case because I can't say I've ever seen every single wiring diagram made by every manufacturer on the planet, but it's very common that you'll find the positive at the top of the page and a negative at the bottom of the page. Like I said, I can't say that they're all done that way, but that is very common, all right? So series, parallel, series parallel. And here you have, I put in some values, right? Okay, so this video series is not just about understanding a series circuit, a parallel circuit, a series parallel circuit, but this video series is also about you creating or you diagnosing these circuits. You want to make your own wiring your own wiring harnesses for your car, the entire electrical system, maybe just one circuit, maybe two circuits. Or you just want to improve your diagnostic ability to check these circuits and test these circuits. Okay, you have to know these values. You have to find, for example, I left this blank on purpose because we're going to calculate this amperage through this ammeter. We're going to calculate the amperage for this ammeter. We're going to calculate the amperage for that ammeter, right? And we're going to change the numbers around a little bit. We're going to calculate the resistance. We're going to calculate the voltage. I'm going to show you different ways of doing that. That's going to go back to some of the first video that I made, and we're going to be touching on Ohm's Law once again, right? In my modified version of Ohm's Law, we're going to be touching on that again in order to do these equations. But anyhow, this is more like I said, not textbook. This is more real world, okay? Now, next thing I'm going to show you is the actual equations for calculating resistances, right, for these circuits. Now, it's going to get kind of, technical, but I'm going to show you a modified version of that, which will make your life a lot easier, right? I call it the calculator version. So we'll get on to that, and let's do it. Okay, so hang with me on this, okay, because this is going to I'm just going to run through this, and it's going to sound like a lot of mumbo jumbo, to be honest with you, blah, blah, it's divided by that, this time, whatever, So we're going to get down to what I call the calculator friendly version. It'll make this much easier for you. And then as we move forward and we get into an analogy and then the actual calculations on the board, we'll be using the calculator friendly version. It makes it much easier. Nowadays, we're all walking around with a calculator in our pocket, basically, also known as your phone, right? That being said, let's go ahead and get through this. The series circuit, as I mentioned earlier, everything flows through each resistance or each load. So to find the total resistance in a circuit, because that's what we need to know when we're selecting the size of the fuse, the size of the conductor, the wire. We have to know the actual current flow or the amperage through the circuit. So in order to know that, we have to be able to calculate the resistance, okay? It all works out in Ohm's law, and we calculate everything. We calculate the resistance, we can calculate the voltage, we can calculate the amperage. But nonetheless, when you're creating circuits, you got to do the calculations. So that being said, the resistance total in a series circuit is simply the resistance of the first, the resistance and ohmage of the first circuit, the resistance and ohmage of the second circuit, or the third, or the fourth, or the fifth, or the 10th, or the 20th, whatever. So basically, let's say we have 3 resistances in a circuit, 3 different loads, or a resistor and 2 loads, or whatever it comes down to, but 3 resistances in a series circuit. Each one's 2 ohms. 2 plus 2 plus 2 is 6. So the total circuit resistance is going to be 6 ohms, right? Simple as that. Series circuit. It's not a whole lot more to be known than that. Just add them all together, right? And once you add them all together, okay, you know it. Simple as that. It's really just that simple. That's great. All right, now, if you don't know, let's say you need to know, let's say there's 3 resistors in a row, 3 resistances. A resistor and 2 loads, 3 loads, whatever it might be. Let's say they're all in series. Let's say you know 2 of them. You know that that's 2 ohms. You know that this is 2 ohms, okay? But you don't know what this one is, right? And I'm making it easy by making it 2, because sometimes it might be 1.7 or 7.1 or 14.9 or whatever it might be, right? But let's just make it easy. 2, 2, and 2. Let's say that we don't know the resistance of one of the loads or one of the resistors, okay? But if we know the total resistance of the circuit, okay, then we can simply just say, let's say, for example, we don't know the resistance of the third resistor. So basically what that means is the third resistor, to calculate that resistance, we take our total minus the sum of resistor number 1 and resistor number 2. Or resistor, another way of looking at it would be to calculate the resistance of resistor number 3, we'll take the resistance total minus resistor number 1 minus resistor number 2, and that'll give us our value. In this case, we know that the total resistance is 6. We know that each of the resistors, number 1 and number 2, are both 2. So 6 minus 2 equals 2. We then know that resistor number 3 will be 2 ohms. So we already, so basically, like I said, so that's really as simple as it is on a series circuit to calculate for unknown resistance or to calculate the total resistance. They're in series, you either add them together, take the total, and subtract the known resistances from the total, you'll get your unknown resistance, right? So it's pretty much just as simple as that. Like I said, and we're going to go over this, and I'm going to explain it further, because like I said, I know I'm going to be saying a lot, and it's going to be like, oh my God, if you're not a math person, you're not a math nerd like me, and some of my friends, then it's going to sound like mumbo jumbo. And I understand that, I do. But let's get through it. I'm going to simplify it, and I'm going to explain it, okay? Now in a parallel circuit, well, it's going to sound even more like that, right? So we're going to take, here's the equation. The number 1 divided by the resistance total is equal to 1 divided by resistance number 1 plus 1 divided by resistance number 2 plus 1 divided by resistance number 3, and so on and so on and so on, right? Okay, now here's a couple shortcuts, right? For example, let's say you only have 2 resistors in a circuit, but this is for a parallel circuit, now keep this in mind. Let's say you only have 2 resistances in a circuit, and both resistances are equal. You have 2 of them, they're both 2 ohms, okay? So now we know we want to find out our resistance total. What you'll do in this shortcut is, you know that the resistance of each of those is 2 ohms, okay? So you plug in the resistance for each of them is 2, not 4, 2. So we put in 2, right? This is for resistors of an equal value, okay? 2 resistors of an equal value. So the resistance is 2, right? The number of resistors or resistances is also 2 because there's 2 of them, 2 and 2. You know that the resistance of the one resistance and the other one are both equal. This one's 2, that one's 2. There's 2 of them. So the calculation would simply be the resistance of one of those is 2. There's a total number of 2. So 2 divided by 2, the total resistance is going to be 1. All right. Now, okay, like I said, mumbo jumbo. So what did I do there? Okay, we have 2 resistances in a parallel circuit, like this one, okay? 2 resistances, okay? We have 2 of them. We want to know what the resistance of the circuit is. We know that one resistance, each of the resistances is 2 ohms. We know there's 2 different resistances. So basically we're taking that known value of 2, because they're both equal, and dividing it by the total resistances. So we have 2 different resistances or 2 different loads. So 2 divided by 2 is equal to 1. So for example, in this circuit, we know that the total resistance in this circuit is going to be 1 ohm. All right, so 1 ohm. All right, so here's another way of looking at that, and I'm going to make it even easier for you. All right, so let's say that these were both 4. Let's say that they were both 6, or they were both 8, whatever it might be, right? If you have 2 loads or 2 resistances of equal value, and there's 2 of them, right? Just take that number right there and times it by 0.5 or half of that number. Let's say that was 6 and 6. Total resistance is going to be 3. Let's say this is 8, 8. Total resistance is going to be 4. All right? It's half of whatever that is. If there's 2 of them and they're equal and it's a parallel circuit, 2 of them equal in a parallel circuit now, whatever this value is, these are both going to be the same. Let's say that was 20 and that was 20. Then the total resistance in a circuit is 10. Okay? 2 equal resistances, 2 of them in a circuit, right? Half of that number is your total resistance for the circuit. It's just that's how it works out. The equation is here. This is your shortcut equation for that. But that's how it works out, okay? So it's as simple as that. That's one of the shortcuts. All right? Now, for example, let's say you want to find, you have 2 resistors of an unequal value, right? And you want to make a calculation. And there's only 2 of them, right? 2 of them. Now these values aren't equal. They're unequal, okay? So a shortcut, and you don't have to do these shortcuts. They're just shortcuts, right? So you'd have your resistance total is equal to resistance number 1 multiplied by resistance number 2 divided by resistance number 1 plus resistance number 2. So resistance total, 2 unequal. Like I said, these are equal, but I'm just pointing at them to show you that there's 2 of them, right? So for example, it was 7 for resistor number 1. The other one was 2, okay? So the other one is not 7, it's 2. So 7 times 2 is 14. So you take that divided by the sum of the 2. So 7 times 2 is 14. Add them together, 7 plus 2 is 9. 14 divided by 9, 1.555555 forever, right? Or round it off to 1.556 or 1.56, right? That would be 14. 7 times 2 is 14. So what we determined here is that our resistance total, right, is, let's say 7 times 2 is 14, 7 plus 2 is 9, divide 14 by 9, 1.55555, like I said. Okay, so, here's something interesting and something you need to remember, all right? So that's the equation for it. And like I said, we're going to do the calculator version. It's easier than this. But nonetheless, that is what they consider to be a shortcut. All right, so here's what I want you to remember. In a parallel circuit, let's say that was 2 ohms and that was 200 ohms, right? Pick a number, but greater than 2, right? When you calculate this resistance, I don't care how you go about doing it. I'm going to show you different ways of doing it, right? The answer is always going to be less than the least resistance, okay? So if you have a 2 and 200, you go, oh, okay, well, what's the total resistance? The total resistance is always going to be less than 2. And as I explained over here, this one, resistance number 1 was 7, resistance number 2 was 2, right? So in this particular equation, we know that one of the resistances was 2, right? And the equation worked out to where the total resistance was 1.556 or 1.55555 forever, right? Okay. So that ended up being the actual value, the total resistance. But as you'll note, 7 and 2, 1.555 is less than 2, right? It always works out that way. If it doesn't, you're doing something wrong. And that's how you're going to know. right? On a series circuit, if you have multiple resistances, right, in order, right, it's always going to be greater than the highest value. For example, let's say that was 2, 7, and there was another one, and it was 9, right? Well, we know that the total's got to be more than 9 because 2 plus 7 plus 9 is 18, right? And it's always going to be more. It's no calculated resistance, no value that you input. It'll always be greater than that value. Always greater in a series circuit and always less in a parallel circuit, okay? All right, that's what you need to know. Now, down on a parallel circuit, to calculate for unknown resistance, let's say that you didn't know the resistance of a 2 resistor circuit, and you didn't know the resistance of resistor number 2. So you take resistance of the total resistance minus resistance number 1 divided by resistance 1 minus resistance of the total circuit, right? Okay. Like I said, this is going to sound like like mumbo jumbo. I have these charts up here for you to take a look at, right? And it gives you an idea what you're doing. But once again, parallel circuit, that's for a 2 resistor circuit. Now, if you had a 3 resistor circuit, keeping in mind a resistor and a load is the same thing. It's just a resistance, right? So a 3, I should have put here resistance as opposed to resistor. But since it's actually drawn technically, they always show them it's just a resistor. That's a symbol for a resistor. I just put here resistor, but in reality, it's just a resistance. Could be the resistor or a load or whatever it might be. Okay, so in a 3 resistor circuit, okay, for example, let's say you want to find out the value for resistor number 3. It's unknown. You would take 1 divided by resistance of resistor. To find for resistor number 3, take 1 divided by resistor number 3 would equal 1 divided by the resistance total minus 1 divided by the resistance of number 1 minus 1 divided by the resistance of number 2, right? Now, like I said, these are what they call shortcuts, okay? For a resistor circuit, you're trying to find for resistance for the resistor of number 4 or the resistance of the 4th load or whatever it might be, right? 1 divided by the resistance of number 4 equals 1 divided by the resistance total minus 1 divided by the resistance of number 1 minus 1 divided by the resistance of number 2 minus 1 divided by the resistance of number 3. Well, that's a mouthful, right? Okay, that's a 4 resistor circuit. Okay, all right. Okay, now keep in mind that when these formulas were created or equations, nobody was walking around with a calculator in their pocket. People were, using a pen and pencil or just a pencil, or I'm not sure what they were using. I have no idea. I have no idea what they were using. But sure enough, nobody was walking around with a calculator in their pocket. I mean, nobody, had a personal computer in their pocket. Absolutely not. So now we do. Okay, so since we do, right, let's not make it so difficult. Let's use what I call the calculator-friendly version. Right, wherein basically, like, you want to know this is for a parallel circuit, okay, parallel circuit. You want to find for the resistance total, or you want to find for the unknown resistance, right? Basically, you're just going to use your calculator, okay? And what I'm going to do is I'll go over this real quick for you. So, calculator friendly, known values. You want to get the total resistance of the circuit. Calculator friendly, unknown value. You already know the total resistance, but you don't know the resistance of one of the resistances or one of the loads. You don't know that resistance. You're trying to find that value, right? So basically, you'll take your calculator, take the number 1, divide it by, in parentheses, right? It's easy for me to say. 1 divided by the resistance of number 1 plus 1 divided by the resistance of number 2 plus 1 divided by the resistance of number 3 plus 1 divided by the resistance of number 4, parentheses, okay? Enter, you now have your total, right? And I'm going to do that. I'm going to use my phone calculator, and we're going to do that exact thing, okay? Just show you just how easy it is, right? Same thing if you don't know the value, you have an unknown value, but you do know the total resistance. Let's say we don't know the resistance of number 4, whether it be a resistor or the load, whatever it might be. But we do know the total resistance, and we know the other 3 resistances of the other 3 resistors or loads in the circuit, okay? So we'll take the 1 divided by, okay, let me start over. Resistance of number 4, the 4th load, the 4th resistor. 1 divided by, in parentheses, 1 divided by the resistance total minus 1 divided by the resistance of number 1 minus 1 divided by the resistance of number 2 minus 1 divided by the resistance of number 3, parentheses. Okay? If you know this, and you have a calculator in your pocket, which you do, most people do, right, then you can calculate these numbers quick and easy. All right? Quick and easy. So, but how did we get here? All right, this is how we got there. Okay, whether it be unknown resistance calculations or known resistance calculations, right? Either way, right? This is how we got to this, right? This just makes it easy. But like I said, keep in mind a few things. It's real simple, right? Like I said before, in a series circuit, the resistance is always greater than any of the individual resistances. Your total is going to be greater. In a parallel circuit, it's always going to be less. No matter how high your resistances go, the lowest number, your total, will be less than that. Okay? That's what you need to know as far as that's concerned. From there, I'm going to move on. I'm going to break this down a little further. I'm going to show you an analogy, okay, that I think will help you maybe understand current flow, right? And then we're going to go on from there. All right? Okay, so if you watched video number 1, you'll know that I'm kind of a fan of the water tower analogy, something I came up with to explain electrical current flow, voltage, amperage, ohmage. But it's also useful here in explaining in a simpler fashion parallel circuits and current flow through a parallel circuit, and why, if you have in a parallel circuit a 2 ohm resistance, a 4 ohm resistance, and a 6 ohm resistance, that I told you that the total resistance will be less than 2. Since 2 is the least resistance in a circuit, you know that the overall resistance must be less than 2. Okay, so let me go ahead and illustrate to you why that is. Keep this in mind, as the ohmage, or the 2 ohms, 1 ohms, as that value goes down, the resistance is less. So the current flow is greater, right? So if you have a 2 ohm resistance and you have a 4 ohm resistance, okay, through the 2 ohm circuit, you'll have twice as much current flow or twice as much amperage as you would in the 4 ohm circuit, right? So a lower number means greater flow, less restriction. All right, so let's look at it like this. Here's what I had done before. We had talked about the water tower analogy, right? So basically, if this was sealed off right here, I plugged this off, you would basically have a column of water. On top of that column of water, you'd have a large reservoir of water with a lot of mass. That mass pushing down on this column of water would create pressure. All right. Now, what we had said was that basically this is a storage reservoir, potential energy. This is your battery. Your battery is electrical energy in storage, right? And what that battery has is voltage or pressure. So we said that voltage was pressure. We basically said that this was going to be our battery. All right. And then from there, once it starts to flow, we open this and we start to get flow. Right, in a system like this where we're calculating flow, we're going to calculate it, let's say, in gallons per minute. And for my metric friends out there, and I didn't do this last time, I'm going to do it this time. Instead of gallons per minute, it would be liters per minute. So 250 gallons per minute would then be 946.3 liters per minute for my metric friends out there. So basically, this, therefore, is flow through the circuit, or through this water circuit, or this water dispersal system, what have you, right? So we know this, since we're looking at current flow, this is now amperage. So in an electrical circuit, this would be amperage. Electrical circuit, that would be voltage, right? In an electrical circuit, that would be the storage energy source, or the energy stored source. That would be the battery. Okay, so now we come down. Now we have a parallel circuit, right? It's basically the same thing, right? So what we have is we have 3 branches or 3 legs, same as we do on an electrical circuit, right? So in this scenario right here, we have a flow meter here, a pressure gauge here, right? Pressure gauge here, and a pressure gauge there. So we're going to monitor all 3 of those legs, all 3 of those branches, right? We know that overall, we're calculating our total flow through that circuit. We're calculating it at 250 gallons per minute, right? This leg, or this branch, is larger than these 2. This one's flowing 150 gallons per minute, or 567.8 liters per minute. This one's flowing 50 gallons per minute, or 189.27 liters per minute. This one is equal to this one, so it's also flowing 50 gallons per minute, or 189.27 liters per minute. Okay, so this is water flow, right? A volume of water under pressure. It's the same thing in electrical circuit, same thing. Battery, energy storage device, right? Pressurized, voltage, ammeter, amperage, right? So in this situation, right, obviously we're going to have 3 legs. This one's going to flow more than this one, and it's going to flow more than that one, right? As a matter of fact, 3 times as much, or therefore these flow a third of this one. Okay, add them together, 50, 150, and 50. Your total is 250. That's basically as simple as that, okay? I also wanted to take note here of your PSI change from here to here, right? So you go from 100 PSI to the outlet of this pipe here, right? Basically no pressure, 0 PSI. it's flowing, but there's no real pressure. It's just flowing, right? Same thing here, right? Pressure drop from here to here, right? Pressure drop from here to here, right? You're on the outlet side of each one of these branches. Basically, you have a flow. You definitely have a lot of flow, very little in the way of pressure, okay? Little to none. All right, so in an electrical circuit, let's change that around a little bit. Let's make it a little bit easier to understand. 12 volt battery, right? Okay. Now we've got our 12 volt voltmeter. We got 12 volts, right? 12 volt battery. Checking voltage right here. We have 12 volts. All right. Now we have our ammeter. We're checking amperage. So still our ammeter right here. Let's just say for this particular circuit we have 10 amps. That's a total flow through the entire circuit. All right. Now that being said, this circuit right here is now going to be 6 amps. And let's see, let me get this on here. 6 amps for this leg. We have 2 amps for this leg. Okay. We have 2 amps for this leg. Okay. So now we just became an electrical circuit. All right. Now we want to figure out resistance. So if the total circuit, the resistance in the circuit is 1.2 ohms. We're having an ohm meter and we're checking the resistance through the circuit. Let me make one notation for you. You never use an ohm meter in a live circuit, right? You're not going to check if this circuit was live and flowing current through it. I would not hook my ohm meter to it, right? You can damage the ohm meter. Don't do that, right? So do not use your ohm meter through a live circuit, okay? All right. So from there, let's go ahead and look at, we've got a voltmeter, we've got an ammeter, we're showing some amperage for each leg, right? Okay, now let's look at the resistance. Okay, so as you can see, the larger leg has less resistance, flows more, right? The current flow through this leg is 6 amps with a 2 ohm resistance. The current flow through this leg will be 2 amps with a 6 ohm resistance, and the current flow through this leg is 2 amps with a 6 ohm resistance, because these two are equal. These are a third of this one. This one is 3 times the flow of these. Okay, so we talked about with the water. All we did is took that water. We talked about the stored water reservoir with a lot of stored energy, right? We then talked about converting that to voltage or a 12 volt battery. Then we took our PSI gauge, our pounds per square inch, right, or our kilopascals, right, and we changed that over to voltage. Same thing with our ammeter. We took gallons per minute or liters per minute, converted that over to amperage. Right, so basically what we're doing here is just changing things around to make it to where, hey, believe it or not, this water column, this stored water source, you know, with big reservoir with a lot of stored energy, the flow through this circuitry is very similar to that of the flow through a parallel circuit, right? All right, so I mean that's what I want you to understand. Now, one other thing I want you to take a look at. See how this is 0 psi, right? And all these legs right here all showed the same, 0 psi. So basically, this would be 12 volts here. This would be 0 volts here, right? 0 volts. So, and this is something else we're going to talk about. Our voltage drop from here to here is 12 volts. 12 volt voltage drop. Basically, we've consumed it, all right? Along each one of these legs is going to be 12 volts. 12 volts here, 12 volts there, 12 volts there. That's nothing more than a branch, right? So each one of these legs or circuits or branches is going to see 12 volts, 12 volts, 12 volts. The circuit itself consumes the voltage. Okay? So here's what I want you to know. If you were to take a voltmeter and stick it here on this circuit, you're going to see 12 volts. If you stick it here, you're going to see 0. The voltage drop will be 12 volts, right? Across the circuit, 12 volts. Okay, now, without getting really technical and deep diving into that, if you want to look up Kirchhoff's current law, also known as KCL, type in KCL current law, and you'll see that basically what it states is this, and how it's relevant to this situation. We have 10 amps of current flow. That means that the circuit itself must consume 10 amps. If there's 10 amps in, there's 10 amps out. The result is always 0. If you have 10 in, you must have 10 out. Positive 10 minus 10 equals 0. All right? So, what do we know? We have 10 amps going in. This leg flows 6, this leg flows 2, this leg flows 2. Total current is 2 plus 6 plus 2 is 10 amps, right? We now know that our calculation is accurate, right? Our resistance in the circuit, like we had shown earlier, is a parallel resistance calculation. Our lowest resistance shown is 2 ohms. Notice that the overall circuit resistance is 1.2 ohms, right? That is our calculation for this circuit, right? And like I said, I think the only thing I didn't mention earlier, I want to go back and just state again, and I may have mentioned it, maybe not, but in this situation, and I want to do this for our metric friends out there, 100 psi in kilopascals will be 689.476 kilopascals. If you, later on in our video series, we're going to have several different topics. One of them is going to be understanding the conversion from SAE or English over to metric. And one of the things we'll be talking about is PSI and kilopascals and things of that nature, right? So in this situation, this pressure gauge would be 100 PSI or 689.476 kilopascals. Now, luckily, right, or I don't know if it's luckily or not, but fortunately, let's say, I don't have to convert anything here, right? 12 volts is 12 volts. I don't care where you're from, right? As far as I know, it could be something I don't know about there, but as far as I know, they're going to use a voltmeter. Whether you're, in a country that uses a metric system or not, you're still going to use a voltmeter. It's still going to be 12 volts. Okay, so I think that that explains a parallel circuit in a little bit better way. Maybe something you can wrap your mind around. Just think about it as branches or legs, right? And keep in mind that when we're monitoring all this or we're testing all this, this circuit is flowing, right? And you never use an ohm meter in a flowing circuit. You want to isolate things, right? In an electrical circuit, you want to isolate things, all right? You don't use an ohm meter in an active functioning circuit. You would use an ammeter in that case, and then calculate the resistance, calculate the ohmage. You do not use an ohm meter in an active circuit. You use an ammeter once again, and you will then take that value and your voltage value and calculate the resistance. Okay? Hopefully that explains things a little bit better. For me, that always helped me, and it's something I adopted years and years ago when I was trying to understand all this. Many, many years ago, I kind of came up with the water tower analogy, and it really makes a lot of sense to me and helped me to understand things much better. So we're going to move on from there. Okay, let me just take a moment here. If you find this content useful or helpful, do me a favor and subscribe to the channel, like and share. It'll do me a world of good moving forward. This is a brand new channel where everything is just getting up and running, and it gives me the motivation to want to do more. I'm going to bring a lot more content in the future. I mean, at this point, if I keep going at this rate, it could be hundreds of videos. I have no clue. But there's a lot to go over when it comes to automotive systems. I'm going to go over all kinds of different things: fuel systems, brake systems, cooling systems, of course, electrical systems. Engine management. We're going to deep dive into a lot of stuff. Transmissions, rear differentials, engines, performance aspects. We're going to get into all that. So, anyways, with that out of the way, do me a favor and go ahead and like and subscribe if you would. So, thank you very much. Okay, so here we go. So, here's our series parallel and series parallel circuits. We're going to do some really quick calculations on what we already talked about. We're going to use our modified version of Ohm's law, right? Pretty straightforward, okay? So we're going to try and find for in each one of these circuits is amperage. So basically to do that, we're going to use amperage is equal to voltage divided by ohmage, right? Or amps equals volts divided by ohms. Simple as that. All right, so we know volts. We know the resistance values. Now we're going to calculate the amperage, okay? So in this circuit over here, this is a series circuit. We have 12 volts. We know that in a series circuit, you add your resistances together. So we have 4 ohms. 12 divided by 4, that's a 3 amp circuit, right? We're flowing 3 amps through that circuit. Okay, in a parallel circuit, we had talked about if you have 2 equal resistances with 2 loads, right? That we know that you can do the calculation, but we also said that what you need to know in this particular scenario is that half of one of the resistances will be your total resistance. So therefore, we know that 12 divided by 1 half of 2 is going to give us 12 amps of flow through this circuit, right? So, as you can see, we've quadrupled 4 times the amperage flow. The current flowing through this circuit is 4 times greater than this circuit, okay? All right, so let's move on a little further. Let's go over to our series parallel circuit. All right, now in a series parallel circuit, what we have to do is we have to calculate those resistances and then add them together, but separately. So for example, we know that this portion of the circuit is a series circuit, right? A series circuit. So we have 1, total 1. We know that this branch of that circuit is the parallel circuit, and we know that that was 1 ohm also. So basically you'll take the calculation from the series circuit, which is 1, plus the calculation from the parallel circuit, which is also 1. We now have 2 ohms in that circuit. So 12 volts divided by 2 ohms is going to equal 6 amps. Okay? So 3 similar looking circuits as far as 2 motors in a circuit, 2 fan motors, 2 fan motors, 2 fan motors. This circuit over here, we added a resistor to it, right? So in those circuits we have 3 totally different current flows, 3 amps, 12 amps, and 6 amps, all right? So this is actually these two, some manufacturers use this exact circuitry to control fan speed. To control the speed of these fan motors, right, they'll actually do it just like this. With being creative with 3 relays, they managed to control these circuits so that on low speed, this is how the circuit is actually routed, or the way the diagram would look. The circuit diagram would look like this, and on high speed it would look like this. So what ends up happening is that in this circuit, right, we have only 3 amps of current flow. In this circuit we have 12 amps of current flow, right? Not only that, what we have is on this leg right here, as we discussed earlier, right, we have 12 volts, right? Oops, dang it, that didn't work. Try it again. This leg, or this splice, or this branch, 12 volts here, 12 volts there, right? In this circuit, we're actually going to have a voltage drop, all right? So our voltage drop across each one of these motors is going to be 6 volts. So we're going to have a 6 volt drop across the first motor, and a 6 volt drop across the second motor, right? They're in series. We talked about Kirchhoff's current law, basically that all the voltage and amperage will be consumed through the circuit. We have 12 volts through 2 equal resistances, 6 and 6. Okay, we can also calculate that. So how do we calculate the voltage drop? Well, we'll do the same thing. We'll use volts equals amps times ohms, right? Okay, well, we know that we want to find the voltage drop across here. We have 3 amps flowing through the circuit, and we have 2 ohms. So 3 times 2 is 6, right? 3 times 2 is 6. So therefore, this motor and this motor will both see 3 amps and 6 volts. Okay, so this would make the motors drive much slower than 12 amps flowing through a 2 ohm circuit. All right, now let's calculate this real quick. Since we have 12 volts going through a 2 ohm circuit, what's our amperage? Right? Okay, well, let's find for amperage. Our amperage is going to be equal to volts divided by ohms, or amperage equals voltage divided by ohmage, or amps equals volts divided by ohms, or whatever, amperes, what have you, So now we know we want to find out what is the amperage through this circuit. Take 12 divided by 2, 6 amps. 12 divided by 2, because this leg of the this branch over here is also 12 volts, because it's just spliced together, branches off both sides. 2 ohms of resistance, we have 6 amps. So what we find is that 12 amps of current flow is consumed 6 amps in this leg, 6 amps in that leg, right? So we have 12 volts with 6 amps of current flow through that motor, 12 volts with 6 amps of current flow through that motor, right? All right, so like we had said before, if we were to use a volt gauge and stuck it right here, it would read 0. Volt gauge and we stuck it right there, it'd read 0. Volt gauge and we stuck it right there, it would be 0, or a voltmeter, okay, voltmeter. All right, so then we know that our voltage drop from here to here is 12 volts. Our voltage drop from here to here is 6 volts, plus an additional 6 volts would leave us with 0 volts, or from here to here would be a total voltage drop of 12 volts. Like I said, with Kirchhoff's current law, we have used all of the available voltage and amperage. Right, we've used it all. We consumed it all. And this also shows that since we have a 6 amp flow here and a 6 amp flow there, and we calculated it at 12 amps total, we know that that's accurate. We know our calculation, that is an accurate calculation. All right, so what about this circuit over here? Let's go to this one. Here we have 6 amps total in the circuit, but we have a 1 ohm inline resistor. Okay, we want to calculate the voltage drop. Well, we have 6 amps times 1 ohm is going to be 6 volts. And also, on this leg, 6 volts, because now we're in a parallel circuit, right? Okay, so now we have, in this situation, we have 6 volts, and we have 2 ohms. We want to calculate the amperage flow through that circuit, right? Okay, 6 divided by 2 is going to give us 3 amps of current flow. 6 volts divided by 2 on this leg is going to give us 3 amps of current flow. 3 plus 3 is 6. So now we know our calculation is correct. But what's something else we noticed here. By wiring it in this manner, no resistance, no resistor required. We have 6 volts going through that motor, 6 volts going through that motor. We're going to have, at that point, let's see here, 6 volts, 6 volts. We have 6 volts with 3 amps, 6 volts with 3 amps going through that circuit. This one has 2 ohms resistance, that one has 2 ohms resistance. Now in this situation over here, since this is in series, right, the current flow through both motors is 3 amps. Same way that this is 3 amps through that motor, and that's 3 amps through that motor. In this series circuit, it's also 3 amps because they're in line, and the total circuit is flowing 3 amps through that motor and then 3 amps through that motor. So in effect, this circuit and the operation of these motors would be exactly the same as this circuit, right? They would act the same. The motors would run at the same speed. They'd run with the same power, right? They have the same current flow flowing through them, right? So basically, here's one way of wiring it. Here's another way of wiring it. But, like I said, through the creative use of three relays, General Motors does it like this, I can tell you for a fact, that they eliminated this resistor altogether, right? And basically just ran them in series for low speed, and then they rerouted the wiring to change the direction of current flow through a parallel circuit. And this is now high speed, okay? And they didn't need the additional resistor or the additional connections or anything else that would be additional to make this circuit occur. So there's less expense, less complexity, right? So by doing this, then they switch over to that, low speed, high speed, right? And that's how it's done. All right, it's interesting how you can manipulate circuits that way, but nonetheless, I think that pretty well covers what I wanted to get to with series parallel and series parallel circuits. Okay, so we have one last thing to go over. I told you when we were going over some of these calculations, I was going to go over a calculator-friendly calculation for parallel circuits. We're going to use my phone or my calculator, if you will. And so basically what we have, here's the resistance formulas that I had shown you, right? And this is what I call calculator-friendly version, all right? And these are the values. So we have 4 resistors in a parallel circuit. Resistor number 1, resistor number 2, resistor number 3, and resistor number 4, right? And as I'd mentioned, those could be loads. Let's just say resistors. Number 1 is 3 ohms, 2 is 6, 3 is 9, number 4 is 12. We want to find for the total resistance, okay? So, like I said, here we go. We're going to take our calculator, and we're going to do the calculation as I had shown you, right? Just to be clear one more time. All right, we're going to do we want to find our total resistance. So we're trying to find for RT. So we'll take 1 divided by parentheses 1 divided by 3 plus 1 divided by 6 plus 1 divided by 9 plus 1 divided by 12 parentheses equals 1.44 ohms. So the total circuit resistance would be 1.44 ohms. So let's put that value right here. We have found for the total circuit resistance, and we know that now that it is 1.44 ohms. And we know that our value is less than 3, so we know it should always be less in a parallel circuit. So 1.44 is our total resistance for this circuit of 4 resistors or 4 loads in a parallel with 4 branches parallel circuit. Okay. Now let's say that we didn't know the resistance for number 4. Like that load or that resistor, we didn't know that resistance. We want to calculate for it. Okay. Once again, same thing. Just going to take our little handy dandy calculator friendly equation here, and we'll do same thing. Start over. 1 divided by, parentheses, 1 divided by, I hope you can see that, the resistance total, which we determined was 1.44, minus 1 divided by 3, minus 1 divided by 6, minus 1 divided by 9, parentheses, and we find that our total resistance, or the resistance for resistor number 4 or load number 4, is 12 ohms. To ensure that we got that right, we already knew that resistance was 12 ohms, so when we did the calculation we came out with 12 ohms, so we know that we calculated it correctly. So 12 ohms. Alright, and that's finding for your unknown value. That's how I did it, right? There's not much more to it than that. Like I said, I wanted to show you earlier how I got there, how I got down to the calculator-friendly version, but now you know, right? And like I said, parallel circuits, calculator-friendly version, calculating for the known value, and calculating for the unknown value, okay? That's how it goes, simple as that. All right, now with that being said, I'd like to wrap this up. I have one final thought I'd like to share with you. Please remember to be thankful, to stay humble, and to show a little kindness in your everyday life. Okay, it'll go a long way for all of us, for yourself and for me and for the whole rest of the world, right? Thanks for watching, and I'll see you on the next one.